and think about how trees get water. So in some coastal redwoods, it has been shown that trees can actually absorb some water from fog. So it is possible that trees can actually take up water directly from air. But by and large, trees get most of their water, regardless of if they have fog absorption or not in their needles. Most of their water is coming from the ground. It's coming from the soil. It's coming from the roots. So this depends on a water potential gradient that exists in plants. And the water potential gradient generally goes like this. You have a negative water potential. That is not an water potential that's expanding like a rubber band, but more of a vacuum-like water potential that is pulling water in the soils. This is why sometimes you can have a bit of soil, you add water to it, and the water just gets absorbed into the soil rather than getting shot out, right? That's a negative water potential. It's absorbing water. The trunk xylem is slightly more negative. It's a little bit more absorbent for water. So water is going to move into the trunk. This is just like a napkin wicking up water from a water droplet on your counter. It's more negative water potential, more absorbent in the napkin, and so water flows in that direction. As you get up to the leaf cell walls, they're even more negative in their water potential, and so they're going to continually pull water up. As you get at the leaf water potential in the air spaces within leaves, there's even more of a negative water potential. And then the outside air is probably 10 times more negative of a water potential than that. So what this creates is a constant gradient of evaporation and wicking from the soil up into the top of the leaf and out into the atmosphere, where water is being pulled from the soil up into the tree leaf and then evaporated out into the atmosphere. So this is really important to understand because those leaves at the very top of the tree are dependent on water being pulled all the way from the bottom. Also, by the time water gets up there to the very tops of trees, it's a pretty dry environment inside those leaves. And they're really dependent on water being delivered from below and not having much resistance to the movement of water through the leaf into the needle and out into the stomata. Remember, the leaf has to open the stomata and it has to lose some water in order to pull in CO2. So it can't simply close its stomata up there and still do well. It still has to bring in some CO2 in order to make a living. In a study looking at redwood height and what governs redwood height, researchers did something really nice, which is that they went along some of these tallest trees and they did some physiological measurements to determine water stress in needles at different heights above the ground. So these graphs and these four panels show different measurements at different heights above the ground in redwood trees. Let's start with the top left panel. This panel is showing that xylem pressure we were just talking about. And what you can see is that as you move into increasing heights above the ground, starting at about 30 meters and then ending at 120 meters, we have increasingly negative water potential. That is, water potential drops. It becomes lower and lower, more and more negative, just like what we were just talking about in the cartoon picture. There are two sets of measurements here, measurements at midday and measurements at dawn. At dawn, plants are a little bit happier because they've had the evening to recover their water status. It's cooler at night, it tends to be moister, more humid, and so the plants have less draw, less demand out of the leaf surfaces. The leaves also tend to have closed stomata, and so because of this, water will fill back up in the plant, and the plant ends up at a better moisture status first thing in the morning. By midday, though, just like when you look at a graph of daily water use in plants, the plants are starting to get stressed out because the air tends to be drier and it's starting to dry out the very tips of those needles. And so those needles have lower xylem pressure and they're under higher stress. But that's increasing as you get to higher and higher heights above the ground. So a needle at the top of the tree is under higher water stress and lower water potential. If we look at the leaf characteristics in panel B, we see that we actually get a really big change in the leaf mass per unit area as we go uh, increasingly from low to high heights, and this becomes important later. So not only are the leaves more stressed, they're actually changing their structure. Essentially, they're starting to look more like desert leaves, where they have a higher mass per unit area, versus low down in the canopy, where they look more like temperate rainforest leaves. If we look at the um, isotope C13 within leaves in panel C, we can see that we get an increase or a less negative C13 fractionation at high heights above the canopy. What this relates to is the amount of conductance or openness of that stomata. And what these data tell us is that essentially a tree that is high up in the canopy has its stomata closed more often. A stomata that is more open will have a lower value for this C13 fractionation. And so that's a really important measurement. It's a technical measurement in tree physiology, but it correlates with the stomatal openness, and you should think of it that way. And so way up in the canopy, these trees have closed stomata, they're high stressed, and they're a little bit different shape. Panel D shows photosynthesis. And what happens to photosynthesis, or P max, as we get higher and higher above the ground? Well, if those stomata are closed, if we're under more water stress, then guess what happens to photosynthesis? It goes straight down. And that's what we see, a linear relationship where as you get taller and higher up above the canopy, those leaves are less happy and they're photosynthesizing less. This is a really nice image from the same paper that produced those figures showing changes in leaf morphology with height above the ground. And notice the difference between the leaves at 112 meters above the ground versus the leaves at 2 meters above the ground. Wow, you would think these are different plants if you just happened upon them. The leaves at 112 meters look like desert plants, like junipers, small leaves, compact, um, not much area per mass. And then the leaves at 2 meters above the ground are splayed out, verdant, large leaves, lots of leaf area, uh, widely spread, thin leaves. And so the plant is adapting to a drier environment. Essentially, the top of the tree is a desert and the bottom of the tree is a temperate rainforest. So what determines tree height? Well, the tallest ever eucalypt might be, let's say it's 119 meters. Many taller have been reported, but not really verified with repeat measurements. So let's say we're around 120 meters for the tallest eucalypt. One of the tallest Douglas firs, the Dorner fir, is 100 meters tall in Coos Bay, but there have been trees in BC where 127 has been recorded as the tallest. A redwood, the current record is around 116 meters as our current tallest. I think we said 115 in an earlier slide, but like we said, that changes from year to year. So the max record is 130 meters or 426 feet, and there are many, many contenders. But what determines this? Well, there's an equation that we can use that relates the flow of water to a driving force governing water transfer divided by resistance. Another way to think of this is that the driving force behind movement of water is related to flow times resistance. If you're fresh out of a physics class, this looks just like Ohm's law. You're used to thinking about electricity this way, where you have a relationship between voltage and current and resistance. This is very similar. It's basically the exact same law. So let's talk about what determines that driving force. Well, it's a little bit easier to think about if we were just hydrologists, just thinking about soil, because there's something called Darcy's law, which is essentially the same law, that describes the driving force. And the driving force is often related to a vertical drop in topographical terms. And so gravity is a driving force for water movement. Well, evaporation is also a driving force for water movement. And so we can think of that negative pressure potential as being essentially the same as the driving force that governs water movement down a slope. So that pressure potential we were talking about, that is our driving force. Water potential is how we refer to this in plants. And it turns out this actually has multiple components. There's a pressure potential that can be generated by gravitational forces or physiological processes. There's an osmotic potential, which can be driven by saltier concentrations of things like salts and sugars dissolved in water. And then there's a matrix potential, which is caused by absorption of water to surfaces. And so if you have a lot of surfaces that the water is sticking to, it's harder to move water um, past those surfaces. All of these in combination result in the water potential that drives water movement in plants. Up to this point, we've primarily been talking about the pressure potential, which is generated as it's a negative pressure potential generated by evaporation. But there's also osmotic potentials and matrix potentials that are important. When we're thinking about those matrix potentials, it's really important to think about the structure of xylem itself. And this is where things can get really technical really fast. So these are some nice images of xylem anatomy. And you can see that there are some differences in xylem anatomy in these two species. But regardless, when we're talking about xylem, we are talking about a series of essentially linked tubes all up the surface, all up the length of the tree. So water has to move through these tubes. And in doing that, there's a lot of opportunities for it to adsorb to the walls and create higher matrix potential. There's also a lot of opportunity for solutes to get in the way and cause issues with water potential. Now, of course, angiosperms and conifers have very different xylem anatomy. That's a subject for another lecture at another time. But that xylem anatomy does make a difference. Larger xylem conduits are easier for water to move through, period. There are some other problems, though, and a reason why some plants, especially in colder climates, tend to gravitate towards smaller xylem conduits or winter dormancy. So what drives resistance? So if we think that water movement is governed by water potential, and water potential can have those three components, well, another component of water, of what governs water movement according to our handy equation, is resistance. So we've taken care of the delta psi there, which is our driving force for water movement. But we know that flow is going to be driven by delta psi, or this driving force, divided by the resistance to water movement. Well, resistance can have multiple components too. Path length can cause higher resistance to water movement. Conduit size, the size of the xylem, is going to cause differences in resistance. So smaller conduit makes more surface content, more adherence to the or adsorption of water to the walls. And shorter conduits means there are more thresholds that the water has to go through as it goes from the bottom of the tree to the top. So it has to cross more barriers. There are these pit barriers between conduits frequently that can cause problems. So all of these things, path length and conduit size, can all cause resistance. So if you have a taller tree, you have a longer path length. If you have a smaller conduit, then you have a higher matrix potential absorption to the surface, which makes it harder for water to move. And if you have shorter conduits, you have more steps that the water has to go through. It has to pass through more barriers to get from the bottom of the tree to the top. So essentially, what we just went through is what governs tree height. So whether we're talking about eucalyptus or we're talking about redwoods or Douglas fir, ultimately, the height of trees is limited physiologically by the stress of the water column. And that magic height that we're finding trees maxing out at, whether it's 426 feet as our potential limit, or even just a little bit higher than that, regardless, that magic height is happening at a place where photosynthesis goes to zero, water stress is at its lowest possible, and leaf mass has hit a physiological adaptive limit. Essentially, at the very tops of those trees, we've hit a desert, and we've hit a desert that can no longer um, support growth of the plant beyond a certain height. It's just too much stress to lift water up that height without all of those forces that are increasing resistance getting in the way. And magically, it turns out that many of our tallest trees seem to fall right in the category of being just underneath what we think the physiological maximum is for tree growth. Sometimes taller trees have been recorded, but not verified often. Trees that have been verified all fall under what we know to be now a physiological limit. There are many other trees, like we started saying at the outset. Trees can be giants in so many ways, and not just height. And so we have all of these giant organisms in the Northwest that may not be the tallest organisms, but they are the largest or the most ancient that we know of. Sometimes those trees are actually even growing on each other, like what happens with this giant cedar. This is one of the Quinault giant cedars here, and along this cedar, which is mostly dead actually, you can see roots and trunks of other species that have colonized the aging carcass of this old cedar. And now what once was just one tree may now be many different organisms. We have blueberry or huckleberry bushes growing up in this tree that are mature and old growth. We have old growth hemlock trees growing on the side of ancient cedars. And so there are layers upon layers of things going on in some of these oldest organisms. This is an image of that. The hemlock tree that's on the right here is actually growing suspended on top of this ancient cedar. And you can see its roots searching for moisture in the mostly dead cedar off to the side. So there are many ways to measure the largest tree. We have some of the tallest trees in the Northwest. We have some of the largest trees in the Northwest. We have some of the densest biomass. But that height, regardless, even in our wet Northwest system, just remember that height is ultimately governed by water stress. You could move to the Southwest and say, okay, is the same thing happening? And I think you'd find the same argument. So you can go to saguaro forests. And yes, there are saguaro forests, forests of saguaro cacti. And there are the tallest saguaro cacti. Where do we find them? In places where the water balance is such that there's a higher supply of moisture in the soils near where these trees are growing. So near rock walls where there can be higher moisture availability or spring availability can allow these cacti to grow a little bit taller, even in a water limiting system where the soil is already starting out at a very negative water potential. So as far as we can get away from temperate rainforests, it seems, in terms of an environment, but still height is going to be governed by water conditions. And when water conditions aren't going to work out, of course, we have catastrophic failure, just like we do in trees. Okay, that's it for this portion of the lecture. Hope you enjoyed it.